All right, new topic, function composition. So the idea with function composition is we start out with our same flowchart diagram for a function where we're putting numbers into this machine, the machine does something to the numbers, and other numbers come out. And maybe to make this a little bit less general, I'll pick a rule for this machine. So we'll say that what this machine does is it takes the input, squares it, and then subtracts 4 times whatever the input was. It turns out that sometimes it's useful to have two of these machines kind of running back to back. What do I mean by that? Think about this diagram where we have some machine, I'll call it g of x. Maybe 5 minus 2x is what I'll use for the rule of this machine. And we take some numbers, like the number 1 for example, and we put it into this machine g of x just like we've been doing. So what will come out would be g of 1, we change all the x's into 1, we do 5 minus 2 times 1. If we put 1 into this machine, I think we'd find that 3 would come out. But that's not the output for the entire machine, that's just the output for kind of this part of the giant machine. 3 comes out, but we're not done at this point. This 3 is on a conveyor belt that feeds directly into this next function, f of x. And since what f of x does is it squares the input and then subtracts 4 times the input, what would come out of this part of the machine would be 3 squared minus 4 times 3. So 9 minus 12. What would come out would be negative 3. In this section, we're going to be taking two different machines like f of x and g of x pictured here and run them kind of back to back where the output from one of them becomes the input into the other one. And really what we're going to do is not think about this like two machines, but instead think about it as one big green machine that we put numbers like the number 1 into, and what comes out as some other number like the number negative 3. Since this big green machine is made up of the blue and the red machines, which are named F and G, it sort of makes sense to name the green machine in terms of the red and blue machines. So what we're going to call this green machine is F of G of X, which is kind of a weird naming convention, but we'll see as we go along why this kind of makes sense. So to see if this is making sense to you, see if you could answer this question. If somebody just wrote this down with no context at all, would you understand what they're asking you? It's a little bit tricky, but what's going on here is there's some machine, the name of the machine is not F or G or H like we're used to, but instead this F of G thing. This is all the name of the machine. And what I'm doing is I'm taking some input, the number 1 in this case, and putting it into this machine. And what the question is asking is, what would the output be? Just like this question is asking what the output of the machine F would be if I put 5 into it, this question is asking what the output of the machine f of g would be if I put 1 into it. And based on this flowchart diagram that I see right here, it looks like the output for the green machine is negative 3. And yeah, there's a lot going on behind the scenes, right? The 1 first changes into a 3, and the 3 goes through another machine, which finally changes into a negative 3. But we're not worried about all the machinery behind the scenes, at least not yet. We're just asking what the output would be for an input of 1. And the answer to that question would be negative 3. If this mathematical statement makes sense to you, you're starting to understand the idea of function composition. A couple comments here. The first one is there's another way to write this machine. This is the standard way to represent function composition, but another way you can write it is with nested parentheses. So the left side of this equation here is completely equivalent to this expression that I wrote right here. More generally, when you write f of g of x this way, it means the exact same thing as writing f of g of x this way. And you're like, all right, weird, 2 ways to write something, I'm not really going to worry about that. Well, actually, you should worry about it because this second way of writing function composition is way more conducive to actually dealing with these kind of problems. Because what happens in a typical problem is you're told what f of x is and what g of x is, and you're asked to evaluate something like f of g of 1. And to answer that question, I guess you have 2 options. You could draw a flow chart like this, and you'd kind of just need to know that you write the G1 first and the F1 second, which is kind of the opposite of what you'd think here. And then you take the input of 1 and run it through this G machine and see what comes out, 3 in this case. And then you take that output 3 and run it through the F machine to see what comes out, negative 3. And for some reason, that would end up being what this expression is asking you to evaluate. I mean, I guess that works, but there's a much easier way. Instead, what you could do is recognize that f of g of 1 is the exact same as f of g of 1, so we could rewrite this question in this format. In case it helps you to visualize things, I'm going to rewrite that with some colors here to try to really emphasize what's going on. But if you're picking this up well, you might not even need this color coordination. The advantage to writing it in this format is all you have to do is work from the inside out. What do I mean by that? If you stare at this thing in red and blue, inside in red here is a question that you already know how to answer. This is just asking you what's g of 1. G of 1 is just asking you the question, what would come out of the g machine if you put 1 into it? If it helps, you can do this off to the side. You can be like, g of x is 5 minus 2x, so g of 1 I would figure out by copying exactly what I see here, except changing all the x's into 1's. So it'd be 5 minus 2 times 1. Well, let's see, 2 times 1 is just 2, so I get 5 minus 2, I get 3. What I'm saying is that g of 1 is the same as 3. And so since g of 1 is the same as 3, what I can do over here is replace where it says g of 1 with the number 3. I'm leaving all the blue stuff alone because I haven't done anything with the blue stuff. All I've done is recognize that on the inside of this expression I have g of 1 written, and since g of 1 is equal to 3 as I showed over here, I can change it into a 3. The nice thing now is if you don't think about how we got here, but you just stare at this expression, you might be able to convince yourself that this is an expression that you know how to evaluate. This is just asking you what comes out of the f machine. The f machine is given by this equation right here. If you put 3 into that machine. Well, that's easy enough. All I have to do is, again, copy this output, except change all the x's into 3's. So I would have 3 squared minus 4 times 3. 3 squared is 9, and 4 times 3 is 12. So I get 9 minus 12, I get negative 3. Because f of 3 is negative 3, this expression here is equal to negative 3. But this expression is equal to this expression, which we said is equal to this expression. So the answer to our question would just be negative 3. If you're kind of clever, you might notice that we really did the exact same thing with this flowchart and down here more algebraically. All right, we first put 1 into g and figured out that 3 came out, so we changed g of 1 into a 3, and then took that 3 and put it into f and found out that negative 3 comes out, which is the same as evaluating f of 3. The key thing here is the answer to this question, f of g of 1, is just negative 3. The way to think about this is all one machine, f of g. It's a strange machine. It has a strange name, not just a single letter, but it's all just one machine. However, that one machine is made up of different parts, and those parts are given to you up here, f and g. And when we put these parts together in this kind of unique way called function composition, really what we're doing is kind of running these two machines back to back. And what we'll see is it's really useful to be able to do that. But the key takeaway is don't think about this like two machines. Yeah, it's created from two machines, but it itself is just a single machine. So since it's just a single machine, we can do all the normal single machine stuff that we've learned in previous sections with it. Let me show you how. Since we can rewrite this f of g of 1 as this f of g of 1, we could rewrite this f of g of x as this f of g of x. Why would you be interested in doing that? Well, because if you work from the inside out in much the same way we did up here, we can replace g of x with what g of x is equal to, 5 minus 2x. So I could say that this expression right here is equal to f of something. That something is g of x, but g of x is 5 minus 2x. So inside the parentheses, I can write 5 minus 2x. And you might be thinking that's really weird, putting this expression into this machine f, but I'd counter that it's really not that weird. We're used to putting expressions into machines. We did it in the previous section, putting like a plus h, for example, into a machine. There's no problem putting 5 minus 2x into this f machine. All we would do is copy this blueprint right here, where the output of this function f of x is x squared minus 4x, except we change all of the x's, the old output, into this new output, 5 minus 2x. So I'd have something squared minus 4 times something, where that something is no longer the letter x, but instead the expression 5 minus 2x. The first step is understanding kind of the how. How was I able to say that this was equivalent to this is equivalent to this? The second step is understanding why. Why would I want to do that? Well, what we just did is came up with a rule for this machine. Remember when I told you to think about this like it's a single machine? Don't think about it like it's two machines. I mean, yeah, it's defined in terms of two machines, but it's all just a single machine. We just came up with a rule for that single machine. What this series of equalities is saying is this machine, when I put x into it, this comes out. Here is the output to this composite machine when the input is x. That's really useful because this question that we already answered above, where we put 1 into a machine, can be done in 2 steps, like I did here, or it can be done in a single step. If this machine is defined with this output for the input of x, it's easy enough to figure out what the output would be when the input is 1. I just copy everything that's in this box, except change all of the x's into 1's. If I simplify this expression, let's see, 1 times 2 is 2, 5 minus 2 is 3. So I'd have 3 squared here. And then over here, I got 5 minus 2 is 3. So I got 4 times 3. I have, let's see, 3 squared is 9, minus 12. I end up with negative 3 as the output. The same output that I figured out up here, but in kind of one step instead of 2 steps. When you're dealing with function composition, you can either think about this new machine in terms of its parts, rewrite it in a different form so that you can kind of work from the inside out to evaluate the output, or come up with a rule so that you're really thinking about it just like it's a single machine, and then you can do all the same input-output stuff that we're used to doing from previous sections. We'll get a lot more practice in future videos, but in this one I just kind of wanted to introduce the idea and show some of the mechanics of function composition.